In this tutorial, I will show you how to do XANES fitting analysis. The purpose of XANES fitting is to quantitatively fit the fraction of different chemical forms of an element within a map. This analysis is done on multi-energy maps, i.e. maps for which you have collected several energies across an element absorption edge. In XANES fitting, we fit the intensity of each pixel as a linear combination of the intensities of reference spectra at each of the mapped energies. This is the same idea as doing linear combination fits of XANES spectra, except that the XANES spectra only have a few points in them. So let's begin by opening a sample. I collected iron maps at several energies across the iron K edge. So I'm going to go ahead and open that now. First, I'll open a single energy. Okay. And now I'm going to go rapid import from, and I'll select all of the energies from this map. Click open. And of course, I want to choose the iron channel to import. And if I scroll down, I can see the 5 different energies that I have collected that go across the iron edge. Okay. All of these maps actually look pretty similar. However, based on principal component analysis, which is covered in a separate tutorial, I know that this sample contains multiple types of iron species. I used PCA to guide selection of XANES points, which revealed 3 different forms of iron. And so I would now like to know the fraction of each of these 3 types of iron that's present in every pixel in the entire map. So before we get started, I'm going to do one processing step, which is, of course, edge removal to make sure I have a nice clean perimeter with no artifacts on the side. And now I'm going to go ahead and go to the Analyze tab and hit XANES Fitting. This brings up a new window where we can go and select the iron channels that we would like to look at. And so now these channels are listed here, and you can see that SMAC automatically reads the energy for each of these different channels. We also have to select the number of standards. Since I said that from PCA we found 3 different M members, I'm going to go ahead and choose 3 standards here. The names of these 3 standards are listed in this box, and they're just given the default name fit 1, 2, 3. I'm going to change this now to M member 1, M member 2, and N member 3. Okay. So notice that SMAC automatically comes up with a box for each of these different M members. We want to make sure that in each of these boxes we have filled in the intensity of the end member spectra at each energy. So the intensity of end member 1 at 7122 eV, 7124 eV, 7126 eV, and so forth. So to fill them in, we will actually go here to File, and we will get the mu parameters. And when we do this, SMAC will automatically find the intensity of each of our M member spectra at each of our 5 energies, and we'll input it into the box. So we're going to do this in a minute, but first we need to prepare our XANES N member spectra. To prepare our N member spectra, we're going to go ahead and calibrate, background subtract, and normalize them using a separate program, the program 6-pack, which is seen here. So first we're going to go ahead and click SAM view. So the SAM view module allows us to load up and inspect our spectra and also calibrate our spectra. So I'm just going to go ahead and add file. And I'm already in my XAS folder, so I'm going to find the correct DAT file. There we go. So this is my first spectrum that I collected from the sample using PCA to select the XANES point. So in order to calibrate this spectrum, I need to load in a calibration foil. So I'm going to go ahead and actually add another file, go back to my XANES window, and I know that I collected an iron metal foil during my run, so I'm going to pull that in. Okay, you can see that I don't have any fluorescence for this. That's the case because the foil was actually collected in transmission, not fluorescence. So I had an iron foil between two ion chambers. And so actually I can find the transmission if I go down to plot type, and instead of plotting μF, which is the fluorescence, I can plot the transmission. In this case, the transmission is in μT2. So I select that, and now you see an iron metal K-edge. I'm going to go ahead and scroll down here, and I'm going to click first for the derivative and replot to look at the derivative of that. Okay, so now to do my energy calibration, I'm going to go to this part of the screen right here, which says E0 calibration. Under actual, so this is the actual value that an iron metal foil should be at, or the calculated value, I'm going to put 7112.0 EV, which is the calculated value for an iron metal. Okay, now I'm going to go ahead and select Find Data E0. Now you see when I do this, SAMView finds the maxima of every peak that it can locate in this derivative. Now, the E0 is defined as the first maximum of the first derivative. And so I want to make sure that SAMView is selecting that as its apparent E0. The red line tells us what SAMView thinks is the first derivative, and clearly in this case it's incorrect. So I want to, that's shown by this red line here. And so I want to move this red line to where the first derivative actually is, which is right here. To do that, I'm simply going to click Previous over here, and you can see that the red marker moves over. Okay, so finally I'm sitting on that first maximum, and you can see that my apparent EV is 7112.8. So I'm shifted about minus 0.8 to EV. Now if I apply the shift to the data, it will apply this energy shift to whichever sample is highlighted in this box here. So now let's click the L5 biofilm R1 sample and just click Apply Shift to this sample as well. I'm going to go ahead and click None and hit Replot. And then I'm going to go ahead and remove this. The last thing I need to do is hit Average Scans, and this will average the spectrum. There's not actually multiple spectra to average over in this example. We've only collected a single spectrum for this particular point. However, we still need to collect average scans because SAMView also converts the file format so that you're able to import it into other modules within the 6-pack program. So go ahead and click Average Scans anyway. Say, yes, save this average. And you can see that it gives us this default name of T2.avg. Actually, T2 stands for transmission, so it looks like I'm averaging the wrong plot type. I'm going to go ahead and click Cancel and hit MUF. There we go. And now my fluorescence actually reappears in this window. So let's try that again. Average scans, save this average. And now I have this underscore fl.avg, and the FL stands for fluorescence. So let's go ahead and save that. Now we can simply remove this file and add our next file, which is this one. I'm going to hit Open. Okay. Now we still have our energy shift recorded here, so all we have to do is hit Apply Shift, Average Scans, save this average, save it, remove file, And I'm going to go ahead, find our last spectrum, hit open, apply shifted data, average scans, save this average, and hit save. Okay. So that's the first calibration step using 6-pack. We can now close this module. And now we're going to go into background removal. That brings up this window. And now we're going to go ahead and click Add Many Files. You'll notice that you're defaulted into the XAS folder again. And you're only showing files of the type .avg, so it's pretty easy to find those 3 spectra that you just saved. So you can highlight all 3 of them and click open, and it will load them up. Okay. So now this is where we do our background subtraction and normalization. There are only a couple boxes that we're actually going to look at when we do the background subtraction here. First, we're going to look at this E0, and then we're also going to look at the pre-edge and the normalization. So let's click on our first sample. If you click raw under plot type, it'll show you the raw fluorescence. If you click pre-edge, it will show you the raw fluorescence with the fit to the pre-edge and the normalization. The E0 is shown by this big yellow-orange dot. You can see that 6-pack chooses default options for all of these parameters. And in general, 6-pack does a good job of choosing default options. So I'm actually not going to change the E0 or the pre-edge region in this instance. However, I don't like how much this normalization line is deviating from the sample. So I'm going to change the normalization from 150 to simply 50 EV. So let's see what that looks like. Okay, and I think that looks quite a bit better. So to summarize, what I'm doing in this background subtraction and normalization is I'm fitting a pre-edge line between -200 relative to E0 and -50 relative to E0. That yields this red line here, and subtracting that off of the data. I'm then fitting a normalization or a post-edge line to the sample from E0 plus 50 EV to E0 plus 245 EV. When I do that, I can now click mu, and this will show me my normalized spectrum. There can be a lot more considerations that go into normalizing XANES spectra. I'm not going to cover these here because these are covered in the EXAFS portion of this summer school. Okay. I'm going to click through, and I'm going to change this, this first point in the normalization to be the same for all samples, so that all of my samples are background subtracted and normalized in a consistent way. So let's see what that looks like. That looks good. That looks decent. Okay. Now if I click and double click and put an X next to each sample, and then I right click on MUI, I can plot all of these spectra together so I can compare them. So let's take a look at this for a minute. You can see that we do see pretty significant differences among these 3 different spectra. That's why they're our iron and member samples. So the last thing to do is to save these normalized spectra. I'm going to click Save MUI. And you can see that it automatically saves this file as a .mu file. I'm going to go ahead and click Save and Place. I'm going to do that for all of them. Okay, great. And now we are done using 6-pack, and we can return to our XANES fitting. So let's go ahead and click File, and we're going to click Get Mu Parameters. And this brings up yet another window. So first, we see the channel listed, and we see the energy that SMAC thinks this channel is at. So if SMAC did not read the energy correctly from the name of your data channel, you could edit it here. For instance, if I'd actually collected 7122.5. Okay, so now you want to select the mu data file. So these are going to be your reference spectra that we just processed. So to select the file, I'm going to go ahead and click Open. And I have to navigate to my XAS folder. And now I see that by default, I'm looking at files of type .mu. So it's easy to find these spectra that I just saved. Hit Open. And then say, yes, I do want to use member 1. Do that again. Open, use member 2, and one more time. Yes, use member 3, and click OK. So now you see these parameters have been updated. Okay, and if I expand the box now, you can see that we can see all 5 energies. So the last thing we can do is go File, and we're actually going to save these parameters and just give it a name like L5 XANES Fit 1 and save. So if you have, say for instance, you collected multiple energy maps for different regions of your sample and you want to do the same fitting routine on all of those different regions, you can then go ahead and load back in these same mu parameters and do the fits using them, so that saves you a step. Okay, so now we can go ahead and click OK here, and it will take a minute. We just have to wait for it to fit. Okay, there we go. When it's done, it will say Fit Complete down here. And then we scroll down, and now you can see that we have 4 new channels. So for each of these new channels, they show the fitted values for each of the reference spectra across the entire map. So this is member 1. All the bright spots show the location of member 1, member 2, and finally member 3. You also have a channel which shows the error on the fit. And what you'll typically see is that the most sort of intense spots, so this is, I'm looking now at just my raw iron channel, you can see that the most intense spots tend to be the ones that are harder to fit. And that's where you see the greatest fitting error. That's pretty typical. So the final step we want to do is overlay these 3 member species. So we're going to go to tricolor plots. And if we scroll down, we can select red, green, and blue. And now we have a new image which displays not just the intensity of iron across the map, but it's showing you the location of the different iron species in the entire map. So you see the location in blue of our 3rd member, the location in green of our 2nd member, and the location in red of our first end member. So this is a very nice way to see how each of the different iron species is distributed across the entire sample area.